The famous 3n+1 conjecture says, start with any number. If it's even, cut it in half. If it's odd, multiply by 3 and add 1. Then repeat. The conjecture asks, does every number go to 1? Nobody knows. We could resolve this conjecture by finding a loop, some number that loops back on itself. That number would never go to 1. So in this episode, we're going to start looking for loops. First, imagine that we always cut numbers in half. We never do 3n+1. So we have an operation sequence here like 1/2 followed by a half, then a half, then a half. So let's check to see if there's a loop of length 4. If we start with some number m and cut it in half 4 times, we'll wind up with 1/16 m. So to locate a loop, we can set m equal to 1/16 m and solve for m. So that's 1 minus 1/16 m equals 0, or 15/16 m equals 0. And the solution to that is m equals 0. And we can check our loops. So sure enough, if we start with 0, cut it in half 4 times, we get 0 at the end. Now that's not exactly the 3n+1 loop we're looking for, but you get the idea. This kind of equation, linear equation, always has exactly one solution. So we just decide on some specific operation sequence, for example, half, 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 and we can easily find the single number that loops back on itself after those operations. What if we take a different operation sequence? Half followed by a half followed by 3n+1. If we start with m and cut it in half twice, we get 1/4 m. And if we multiply by 3 and add 1, then we get 3/4 m plus 1. So we call that the composition of those operations. Now to find a loop, we ask what m, if we send it through 3/4 m plus 1, do we get the same m out? So m equals 3/4 m plus 1, which gives m minus 3/4 m equals 1, which is 1/4 m equals 1, so m equals 4. And we can check it. So if we start with 4, cut it in half, gives 2, cut it in half again, gives 1, and then 3n+1 it will bring us back to 4. Hey, we found a loop already. It's 4, 2, 1, 4, 2, 1, 4, 2, 1. Now, we kind of already knew about that loop because it involves 1. And we're looking for a loop that doesn't involve 1 so that you can write this paper. The 3n+1 problem has a loop by you. Okay, let's solve for another loop of length 3, this time with the operation sequence 3n+1, a half, and then 3n+1. So here the composition of these operations is 9/2 m plus 5/2, and we can solve for m equals that. And the solution is -5/7. So let's check it. Sure enough, if we take -5/7 and apply this sequence, we get -8/7, -4/7, and then -5/7 back out. So that's a loop that doesn't involve 1. But we don't care about loops involving fractions either. So back to the drawing board. How about a loop of length 5? So there's actually 32 different operation sequences that we can try. Maybe the first one we try is 3n+1 followed by a half, followed by 3n+1, and then a half and a half. So what number, if you put it through this operation sequence, do you get the same number out? Using the same method, we'll find out it's -5, and we can confirm that. When we apply the first operation, 3n+1, to -5, we get -14, and so on. So we get another loop. But we don't care about negative numbers any more than we care about fractions. But actually, this is a positive loop for the 3n-1 problem. So start with 5 times 3 minus 1, 14, then 7, then 7 times 3 minus 1 is 20, then 10, back to 5. So we found a valid loop for the 3n-1 problem. And we can use the same method to find a valid loop for the 5n+1 problem. With the operation sequence, a half 5n+1, a half 5n+1, and so forth, we can solve for m equals that, and we get 26. That means if we put 26 in, we're going to get 26 out. And sure enough, you can follow the path: 26, 13, 66, 33, 166, 83, 416, 208, 104, 52, 26. So we found loops so far for the 3n-1 problem and the 5n+1 problem. Now if we could just find a loop for the 3n+1 problem. It seems like no matter what operation sequence we tried, we always get some fractional number or some negative number. So let's try this operation sequence: a half, 3n+1, 3n+1, a half, 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 3n+1, a half, and solve for n equals that. If we do that, hey, we get 8, and we can confirm that if we put in 8, we get 8 out again, and the sequence is 8, 4, 13, 40, 20, 10, 5, 16, 8. Looks valid. It's a positive loop of numbers that don't involve 1. But it's not valid. There's actually a mistake here. You can pause the video if you want to find the mistake yourself. It's here. Look, we turned 4 into 13, but 4's even should become 2. I call this an imposter loop. We can fix it. So from now on, let's tighten up our 3n+1 sequences like we talked about in previous episodes. We know 3n+1 yields an even number, and we're going to cut it in half anyway, so instead of going from 5 to 16 to 8, we skip the unnecessary step and go directly from 5 to 8. The new rule is if a number is odd, multiply by 3 and add 1 and immediately cut in half. And this will get rid of our imposter loops. Okay, to summarize, we found loops for the 3n-1 problem and the 5n+1 problem using a simple solve for n strategy. But we still didn't settle the 3n+1 question. So stay tuned. Next episode, we're going to get serious about finding a 3n+1 loop.